point cosmic microwave background. And because of the observation of cosmic microwave background, it's sure that the universe was dense and hot in the beginning. And also by measuring the expansion rate, we can convert the Hubble expansion rate to density components. It's one-to-one correspondence. So from observation now we know very well about the dominant component of the universe. So we know that in the beginning the universe was dominated by radiation, and slightly before the epoch of recombination, the universe changed to matter-dominated phase. And now we are in that kind of dominated phase. So this is summary. And about coming back to the gravitational wave, we can observe much further using gravitational wave. And there are events which happened much before the epoch of recombination. But they are all theories. There is no direct observational evidence here, so they are all theories. But they are quite motivated by some indirect observational facts and also some implication from particle physics. So I'm gonna explain those events from now. And this inflation limiting cosmic phase transition, they all may produce gravitational wave in the universe. So maybe in future if we can observe gravitational wave from here, that's the oldest signal the human being can have. So yeah, I'm gonna talk about the theories of the early universe, which I showed here. Okay. So let me start from inflation. So this is the blue sky map of cosmic microwave background by recent Planck satellite. So you see the temperature of the photon is 3 Kelvin plus minus 10 to minus 5 Kelvin. So the fluctuation rate is very tiny. And here people got the question, why the universe is so uniform? And what's the origin of this small temperature fluctuation? And the inflation can solve this question. Maybe I should explain this first question more details. So this is blue sky map. So for example, this point and this point is 180 degrees different. So we are observing this direction and this direction, and the universe looks the same. But these photons just arrived us. So why this universe knows the temperature of that universe? So if we can have interaction, or if they can have interaction before, then it's natural that temperature is the same. But it seems that the photon just arrived here, so they don't know the information each other. That's the question. And to solve this problem, we need inflation of the universe in the very beginning of the universe. So let's consider arbitrary initial condition. So let's say in the beginning of the universe, this is the region of causality, Hubble horizon. So inside this circle, particles can have interaction with each other. So it's natural that they have same temperature. But outside the Hubble horizon, the temperature is the same. So it can have different temperature. And if we consider the expansion of the universe, if we expand this up to now, then in terms of standard expansion history of the universe, then we get this number, 2 degrees in the sky. So 2 degrees is very small in the sky. So inside this 2 degrees, it's natural that the universe has same temperature, but not the other. And the idea of inflation is that let's expand it dramatically at the beginning of the universe. Then we get the uniform universe. This is the idea is very simple. So by changing the word, here I show the history of Hubble horizon. So horizontal axis is scale factor of the universe, and the vertical axis is physical scale. So any types of scale is okay. You can take it like wavelengths of gravitational wave or whatever. You can just it's just this green line just shows the distance of two objects. And we are here today. So Hubble expansion rate behaves like Hubble horizon grows at a to 3/2 or a square. Depending on if the universe is radiation dominated or matter dominated. This can be obtained from Kuroyanagi equation. So this is the growth of the Hubble horizon, which we know from standard Big Bang cosmology. And the problem is that here we observe, let's say this corresponds to 2 degrees in the sky. We observe much larger 2 degrees of the sky. Then this was outside of the horizon. So this Hubble horizon corresponds to the causality region, as I said. So the scale which is smaller than this Hubble horizon, this region, can have interaction with each other. But above this red line, the things cannot interact with each other. So the problem is that this object comes from the outside of the horizon. So this didn't have interaction in the past. But if we consider inflation of the universe, then the Hubble horizon is constant during inflation. This I will explain tomorrow in details. But if we have this phase of inflation, then this line comes inside the causal region in the beginning of the universe. So this solves the problem. So the idea is that originally this object, two objects was inside the causal region, but it was expanded dramatically because of inflation. So it gets out from the causal region, and after inflation, it comes back to the region of causality, and that's what we observe, and that's why we observe the uniform universe. So as far as I know, this inflation is the most successful theory to solve this problem, and it's widely believed in the community of cosmology now. And during inflation, let's consider quantum fluctuation during inflation. And this fluctuation, small fluctuation, is expanded by inflation. And so the size was very tiny in its quantum level during the inflation. But after the inflation, it stretched to the classical size. And this is what we can observe as gravitational wave. And inflation predicts not only gravitational wave, but also density perturbation. And this density perturbation, is considered to be the origin of this temperature fluctuation in the CMB. And the prediction, theoretical prediction from inflation theory has a very good agreement with observation. So now many people believe that the origin of density perturbation is in inflation. So it's not very exotic that we also consider gravitational waves from inflation in the similar mechanism. Okay. So inflation, as I explained, is accelerated expansion. And because this dramatically expands the universe becomes very cold. Everything is diluted after inflation. But what we know from the CMB observation is dense and hot universe. So at the point here, universe should be dense and hot. Otherwise, we cannot explain the existence of cosmic microwave background. So we need some mechanism to heat up the universe, and that is called reheating. And this is completely motivated by theory. There is no observational implication for reheating, so we don't know what's the mechanism of this reheating. So in that sense, this reheating may also produce gravitational waves. So in that sense, it's very important to search for the gravitational wave from this reheating. And after reheating, the universe becomes hot. And as the universe expands, the temperature goes down. And according to the grand unification theory, the universe, the force was unified at high temperature in the beginning of the universe. But eventually, as the temperature of the universe goes down, the force is separated eventually. And this, at the time of this separation, the property of the vacuum of the universe change. And that is called cosmic phase transitions. And depending on the models of the phase transitions, the universe, this phase transition produces gravitational wave. So, yeah, here I show the summary of what I talked gravitational wave generation. So there are several mechanisms, events to produce gravitational wave in the early universe. And in terms of equation, the mechanism to produce gravitational wave during inflation and the other event is different. So here again we see equation of gravitational waves. And the gravitational wave from inflation originates from quantum initial condition which is determined by this quantum fluctuation. And there is no matter term on right hand side when we compute the gravitational wave from equation. On the other hand, for other mechanisms, gravitational waves are sourced by this matter term. This is anisotropic stress from matter component.